Dear students, myself Dr. Sritama Datta, Assistant Professor, Swami Vivekananda Institute of Science and Technology. Today's topic is wave optics. In this lecture, we discuss about the diffraction of light. First thing, we have to know what is diffraction of light. When a beam of light falls on a sharp edge of an obstacle or a narrow slit, the condition is where the size is comparable with the wavelength of the light, there is a departure of straight line of propagation of light and light bends round the corners of the obstacle or slit. This phenomena is known as diffraction. So, diffraction can be classified into two broad ways. One is Fraunhofer diffraction and other is Fresnel diffraction. What is Fresnel diffraction or what is Fraunhofer diffraction? What is the difference? In Fresnel diffraction, the source of light or screen or both are at finite distance from the narrow screen. Whereas in Fraunhofer diffraction, the source of light and screen are effectively at infinite distance from the narrow slit. Now we have to learn the salient feature of Fraunhofer diffraction. What is the salient feature? First thing, incident and emergent wavefront are plane vectors. Number two, wavefront incident on slit and screen is infinite. And lastly, the convex lenses are required to observe diffraction pattern, to observe the Fraunhofer diffraction pattern. Here we show the single slit Fraunhofer diffraction pattern, diffraction experimental pattern. So this is the source, this is slit, and this is the screen, and we use the convex lenses in this position, and theta is the angle of diffraction, and we get the diffraction pattern. Now we reduce the wave equation, that is Ka sine alpha by alpha sine 2 pi by small t by t minus r by lambda, where A is the slit width and alpha is dependent on the theta, that is alpha is equal to pi a sine theta by lambda. Alpha is the parameter which is dependent on the theta value, angle of diffraction. So we get the wave equation of the single slit diffraction pattern. So the intensity will be proportional to amplitude square. So here is the intensity value, that is I naught sine square alpha by alpha square. Now we have to calculate the intensity of the central maxima, position of the secondary minima and position of the secondary maxima. So to know the intensity of the central maxima, if theta is equal to 0, this is the diffraction pattern of the single slit diffraction, single slit diffraction, Fraunhofer diffraction. Here is the central fringe. Here is a central fringe, and there is a maxima and minima, secondary maxima and minima. This is the diffraction pattern in the screen. So the central maxima is a intensity is high, that is I naught. I naught, that means I naught means that is k square a square is the I naught. The intensity of the central maxima. The position of the secondary minima is, if sine alpha is equal to 0, from that we derive alpha is equal to n pi. N is a order number, that is 1, 2, 3. So we get the position of the minima at pi, 2 pi, 3 pi and so on. And this is the condition of the secondary minima. For secondary maxima, we get sine alpha is equal to 1, that is maxima, and we get alpha is equal to 2n plus minus 1. Exactly the same way we get the position of the secondary maxima, and this is the condition of the secondary maxima. Now width of the secondary minima and secondary maxima. First, secondary minima. Y is the distance of the nth minima for the center of the screen. From the condition of the minima, we get sin theta n is equal to n lambda by a, and if theta is very small, we get sin theta is equal to y by d. Equating the both equation, we get the width of the secondary minima is lambda capital D by A. A is the slit width, D is the distance from the slit to screen. In similar way, we have to find out the width of the secondary maxima, and we also find that this is lambda capital D by A. So the width of the secondary maxima and the secondary minima are same. Thank you.